want to, you have, and most of us know Mark. You see him, he's a liturgist here. Uh, that's not what his PhD is in, but that's what he does here. He's on the session, has been on the session. He's a Foundation Distinguished Professor of Sustainable Engineering and your editor for Journal of Ionic, not Iconic, Ionic Liquids here at the University Institute for Sustainable Engineering. He's presented with us before, and he spent time to put this presentation together, and we really appreciate you, Mark, doing that and giving us the time. So let's just begin and go for it. Thank you much.
Well, Thad, thank you for the invitation to speak, and it's not often that you get to speak in front of your church family, so I really appreciate you being here today. As Thad said, my name's Mark Shiflett. I was just telling some friends that I'm not native of Kansas. Actually grew up in North Carolina and went to the University of Delaware where I got my PhD. Worked for the DuPont company and then retired and became a professor. Today's talk is about work I did both at DuPont and also what we're working on at the University of Kansas. And so the title is History and Future Possibilities of Air Conditioning and Refrigeration in a Warmer Environment. So just briefly, this is where I spent kind of the first 30 years of my career. It's called the DuPont Experimental Station. DuPont's the oldest operating company in the U.S. They were founded in 1802. E.I. DuPont moved over to the United States from France. He studied under a chemist named Lavoisier. Lavoisier was the person who discovered oxygen. So when E.I. came to the United States, he was able to make gunpowder. And he made some of the purest, the best gunpowder that could be made in the United States. So the U.S. government, Thomas Jefferson, told him, I'll buy every pound that you can make. So when you're in new business and you get the U.S. government to tell you that we'll buy every pound you can make, that's a pretty good proposition. So that's now led to that company being very successful over 250 years. When I joined in 1987, it was all about the story I'm going to tell you regarding refrigerants. Like I said, I retired. My wife thought we were retired, but I was too young to maybe just run and bike, and so I thought, well, I'll be a teacher. And my only regret is that I didn't do it sooner. I loved working at DuPont. I loved the people. But there's really something special about being a teacher and helping this next generation of people become engineers and become scientists. So today's outline, I'm going to tell you a little bit about how does your refrigerator work. You might know, but it's part of the story around refrigerants. And then I'll give you a little bit of history about refrigerants. I'll tell you about a project we're working on at the university called Earth. And then we'll wrap up with a few concluding remarks. So this is your refrigerator. And this certainly looks familiar to you, looking in through the doors. And so this is a schematic of the refrigerator. So depends on the model, but let's just say this particular model in the freezer is at the top. So you're going to have some tubes, some little tubes that run back and forth inside the freezer compartment. And inside those tubes is a gas. And that gas is called a refrigerant. And that refrigerant is what's moving the heat from the cold to the hot. So everybody knows if you take something cold and something hot and put them next to each other, the heat will transfer from the hot to the cold, right? Due to the difference in temperature. So this gas that's running through these tubes, there's also a set of tubes either on the back of the refrigerator or underneath the refrigerator. And if you go home and put your hand behind your refrigerator or underneath it, it'll probably feel warm, right? And that's heat that's being pulled out of the inside of the refrigerator and being expelled to outside the refrigerator. And so that's the transfer of heat from inside to outside. And that's how the inside of the refrigerator is staying cold, because the heat inside the refrigerator is being pulled out and it's being expelled outside. And the way that heat is moved is using a gas. And there's something in the bottom of the refrigerator that's called the compressor. And you can almost think of it as a pump. And this pump is pumping the gas around inside these tubes. So if we just start with the compressor and we're pumping the refrigerant up to the cold part, it's absorbing the heat. And then as it comes down into this part, which is outside the refrigerator, is expelling the heat. And every refrigerator, every air conditioner basically works the same way. Your car, you have this part that sits right behind those little vents in your dashboard. And this part sits in the front where your radiator is in the front of the car. And it's pulling heat out of the passenger compartment and it's pumping it outside the car. And the compressor sitting under the hood. Your home, if you have an air conditioner for your house, you have that thing that sits outside the house that's got a fan on top of it. And you have something else that's sitting inside your house, usually close to your furnace. And if you have central air, air is being pulled through the ducts and taken down either to the basement or the attic. And that evaporator, this thing up here, is cold and absorbing heat out of the air in your house. And then the refrigerant, the refrigerant gas is moving outside to that outside unit. And there's the compressor, and there's also this, and that's expelling the heat outside your house. If you have a heat pump, it works actually the opposite way. The unit outside gets to a temperature that's lower than the outside temperature, so it can actually pull heat out of the outside and bring it to the inside. So basically every air conditioner, every refrigerator works this way, and they all use a refrigerant. And we'll talk about this. There are a lot of different types of refrigerants, depending on the application, whether you're using it in a refrigerator, using it in a car, using it in a supermarket, using it in a truck that's going down the highway. All of them use different refrigerants. So let's do a little history. Let's go back to the 1800s. This is what you might have had in your home. Maybe your great-grandparents probably had one of these, an ice box. So ice was harvested out of lakes and ponds. It was stored even during the warmer months, hopefully not melting if you stored enough of it. And picture of children delivering it. And then you had a block of ice that sat inside the ice box. And that's what provided the cooling. It worked, and you could have perishable foods in your home, but it wasn't very efficient because you've got this giant block of ice that's melting, making a lot of water. You got to replace it probably once a week. If someone didn't show up with the ice, obviously everything in your refrigerator quickly spoils. So, but that's what we had 1830 to 1850. So in between then and 1920, electricity came along and homes started to be electrified. And so now General Electric gets involved in trying to make the first refrigerator that would run on electricity. And this refrigerator is almost the same as this one today, the way it was designed. It had a compressor, it had an evaporator, it had a condenser, moving heat from inside to outside. Not a lot of difference. You could get it in some nice colors like lime green and burgundy, along with white. So this is what was called the monitor top refrigerator. And actually there's the ice box. All it could do was just have some ice, maybe ice cubes in an ice tray. And then the rest of it was more or less like a refrigerator. So What did they use for the refrigerant? So this is the gas, again, that circulates around inside the tubes that I was telling you about. If you open the door, you're not exposed to it, but it is inside these little tubes that are running inside here and then along the back and to the compressor and back to here. So this is the chemistry lesson. So I am a chemical engineer, okay? Some of these you may have heard of, ammonia. I'm sure you've heard of ammonia. Sulfur dioxide, that has a really strong smell like eggs, rotten eggs. And then methylformate, methyl chloride. This is what they were working with. This is what they had. They worked, but they were toxic. If anybody's worked with ammonia, you know it's pretty toxic. They were corrosive and they were flammable. But this was the best they had. And honestly, this was a huge advancement over, over this, right? This is a huge step forward. So people were willing to have these kinds of gases inside the refrigerator. Problem is that they do leak. And I'm sure a lot of you have experienced either a refrigerator that stopped working or an air conditioner that stopped working because the refrigerant inside leaked out. It's a gas, it's under pressure. If there gets to be a small hole, maybe even due to corrosion, the gas will escape and then you have to get it fixed and you have to get it recharged. If these gases leak out inside your home, like ammonia, you're going to know it right away. Like you're going to be like, whoa, something's not right. I got to leave this room. But if you're not home and your pet or your child, like it could be really dangerous. So we needed to find some better solutions. So Thomas Midgley, he was a mechanical engineer and a chemist, and he worked for General Motors in what was called their Frigidaire division. And I would claim he was a chemical engineer because he was both a mechanical engineer and a chemist. And he looked at the periodic table. So this is just a small little part of the periodic table that has all the elements. And he started to look at these gases that they were using. And he said, well, we have nitrogen, and we have hydrogen, and we have a carbon, and we have an oxygen, and we have a sulfur, and we have a chlorine. And so he noticed there was kind of a pattern here. And it made him wonder, like, well, why do we not have a refrigerant that has this element, fluorine? And so it made him think, well, maybe we can design some new refrigerants that use fluorine instead of some of these other elements. And so he was the first to come up with this idea of using what are called chlorofluorocarbons. So you may have heard of this, CFCs. He was the first to invent this dichloro-difluoromethane. So that molecule looks like this. It has a carbon in the center, it has 2 fluorine atoms, and it has 2 chlorine atoms. And what he discovered was that it was a very good refrigerant. It had a low boiling point. So when this substance boils, it's about minus 29 Celsius. So whatever that is in Fahrenheit, you know, minus 35 Fahrenheit or something. So it's very cold. So when it's boiling, it gets very cold, colder than, you know, ice, which is at 32 Fahrenheit. So it could make a good refrigerant. And more importantly, it was non-toxic, it was non-flammable, and it was safe. So remember, the other refrigerants were toxic, like ammonia. They were flammable. Here you have now a new gas that can work as a refrigerant that's non-toxic and non-flammable. Now this is General Motors. So General Motors doesn't make chemicals. DuPont and General Motors had a lot of relationships. DuPont made like all of their lacquer paints for all of General Motors cars. So General Motors goes to DuPont and says, if you guys can make this, same story as we started out with at the beginning, we'll buy every pound you can make. Why? Because they had a vision that cars were going to have air conditioners. And they were even interested in making refrigerators with this. So the DuPont company gets into an agreement with them, and they start manufacturing these chlorofluorocarbons. And so the first one we talked about was this one. But it turns out there were a whole family of chlorofluorocarbons that could be made, and they had different properties. So you can see you have minus 29 C boiling point, plus 24 C boiling point, plus 48 C boiling point, minus 49 C boiling point. Based on those different boiling points, that led to different applications. So originally we were looking at refrigerators. Chillers were used with this refrigerant here that we refer to as R11. And that would be used for cooling like big buildings, like this church might have a chiller, or certainly buildings like over at KU would have chillers. It would be a whole lot more energy efficient to use something like this than it would be to try to put an air conditioner in every window. This is electronics. So electronics were starting to come online. And when you made electronics and you had circuit boards and you put all the little diodes and transistors and resistors into the circuit boards and you soldered them, it left a lot of flux on the circuit board. So all circuit boards were washed with this particular chlorofluorocarbon because it boiled at about 50 C, right? Which is warm but not so hot that it damaged the boards, and it would remove all the flux. And so this was made in millions, all of these were made in millions and millions of pounds. This one, because it had such a low boiling point, used in supermarket refrigeration. So there where you really want things to be frozen, stay frozen, you need the temperature to be very low. So now you've got these four, and there's many more for a lot of other applications. So let's fast forward to the 70s. So these three scientists, Paul Crutzen, Mario Molina, and Sherwood Rowland, they came up with a theory. And their theory was that these chlorofluorocarbons were damaging the Earth's ozone layer. And so the Earth has a troposphere, and then the outer part of the troposphere is where the ozone layer is. So, well, what is ozone? Ozone is almost like oxygen. You know, oxygen is basically O2, but ozone is O3. And ozone, which is in this outer part of our atmosphere, protects us from UV light. So as UV light from the sun, UVA and UVB and even UVC light come from the sun, the first thing that those rays encounter when they come to the atmosphere is our ozone layer. And those UV rays break down ozone, O3, into O2, oxygen, and O dot, which are called radicals, oxygen radicals. And these oxygen radicals are really reactive, and all they want to do is find an oxygen and make O3 again. And so this is constantly going on in the upper part of the ozone layer. Ozone breaking down in oxygen and oxygen radicals and oxygen going back to ozone. And that's the way the ozone layer works, and it prevents a majority of UV light from hitting the surface of the Earth. Without the ozone layer, there'd be no life on Earth because there'd be way too much UVA, UVB radiation. We probably feel the effects of maybe 3–4%. The other 95+% is being absorbed in the ozone layer. So again, without an ozone layer, no life. Plants couldn't survive, animals couldn't survive. Without plants and animals, humans can't survive. So their theory was that in these chlorofluorocarbons, they have a chlorine, and because the molecule is so stable, if it leaks out of a refrigerator, it can make it all the way up to the ozone layer, which is tens and tens of miles above the Earth. Most things come back into our atmosphere. If something's released from the surface of the earth, it comes back in the rain, it comes back in a variety of ways. But these molecules, because they're so stable, could make it all the way to the ozone layer. And then when they made it to the ozone layer, the UV light would break down this chlorofluorocarbon, releasing the chlorine and disrupting this equilibrium. So ozone could make oxygen and oxygen radicals, but oxygen and oxygen radicals could not make ozone. So it was like a one-way street now. This can go to this, but this can no longer come back to this. And this was their theory. And they published it in, I think Science, Nature. They published it in a magazine called Nature. So everybody said, you're wrong. That doesn't happen. Especially people using refrigerants and people manufacturing refrigerants and companies building refrigerators and air conditioners and everything else, right? Because by now we're talking about billions of dollars of business around the world. And here these three are saying, no, there could be a problem here. Now there's a corollary to that today, right, with global warming. I'd say some people believe it, some people still don't believe it. So 1974. So let's go forward 10 years to 1985. 1985, Joe Farman, Brian Gardner, and Jonathan Shanklin have now the ability to measure ozone in the ozone layer. They've made some instruments that they can put on these weather balloons that they can launch over the Arctic, and the weather balloon will carry this instrument high enough that it can measure the concentration of ozone in the ozone layer. And what do they discover? The ozone concentrations over the poles are starting to decrease. And the reason the poles, where it happened first, is because as gases and things get released on the Earth, the way the weather works is it kind of brings a lot of things to the poles first. So if you're looking for very small concentrations of something, you're usually going to find it in the highest concentrations at the poles first. And so that's where most of the CFCs, these refrigerants, were accumulating, and therefore the ozone concentrations were decreasing the fastest over the poles. So now we have experimental evidence that the ozone concentrations are actually decreasing. And interestingly enough, 1985, I started at DuPont in 1987. So only 2 years after this discovery. And I remember people saying, well, who cares? Because nobody lives there. If the ozone concentration over the pole decreases, the only thing it's going to affect is some polar bears. I remember this. All right. Well, trouble is those ozone holes started to get bigger and bigger. And then they did start to touch land masses where people did live and people did care, like the tip of Australia and Greenland. And remember, I said without an ozone layer, you can't live on the Earth. And our ozone concentrations are declining. Well, it was pretty serious. And here I am, a 20-year-old something engineer coming into the DuPont company, getting to work on this problem with hundreds of other people, because we didn't know what would we replace these refrigerants with, and we needed them, right? You need them for transportation of foods and medical care, and for a lot of reasons you need cooling. Well, it was a serious enough problem that 197 countries came together in Montreal, Canada in 1987. I was working at DuPont when this happened, and they signed what was called the Montreal Protocol. And they agreed we're going to phase out these chemicals that are depleting the Earth's ozone layer. And I also remember thinking, how are we going to do that? And I remember some management in DuPont saying, Well, we made hundreds of millions of dollars on selling chlorofluorocarbons. Let's just get out of it. We've made our money. Let's just walk away from it. Let somebody else spend the millions and millions of dollars it's going to take to try to figure out how to solve this. There were also management that said, nope, we're going to figure this out. If anybody can do it, we can. And I still remember those people to this day because they made a really important decision because a group of us had to figure out how to do this. And we did. So now there's a race to figure this out because we've got to phase these chlorofluorocarbons out. They're in every car, every refrigerator, every air conditioner, every supermarket, all over the entire world. And we got to phase these things out as fast as possible. So what did we do? Well, we knew that the chlorine was the issue in the ozone layer. So let's just eliminate the chlorine. Let's just get rid of the chlorine. So we first came up with these hydrochlorofluorocarbons where we took one chlorine away and we replaced it with a hydrogen. And that was a pretty good idea. This ozone depletion potential, we could reduce that by 95%. So we're reducing it by 95%. Part of the problem was the properties change a little bit. So you don't have exactly the same boiling point anymore. Minus 29 Celsius versus minus 41. There are a lot of applications where that's not going to work. And people wanted replacements that were like drop-ins. Because if someone comes to your home and you just bought an air conditioner a year ago, and now that refrigerant is going to be phased out, the last thing you want to hear is that you got to replace the entire air conditioner. You would rather just replace the refrigerant. So we had to keep thinking about it and working on it. And so we developed what were called hydrofluorocarbons, and those had no chlorine, but they were a little bit more complicated to make. Because you can see, like, this has got one carbon with 4 other atoms, so there's only 5 atoms here. Now we're talking about 2 carbons and 6 other atoms, so now we have 8 atoms versus 5 atoms. So just on an atom basis, a lot more complicated to make. It took a lot of research to figure out how are we going to make these in hundreds of millions of pounds. So a chemist will figure out how to make this much of it. And then they hand that to me, and they say, okay, Mark, you figure out how to make 100 rail cars of it out there. Challenge. But we figured it out. And we started producing like this particular refrigerant that had 0 ozone depletion potential, and it started going into every car and every refrigerator. And we said, hey, you know what? We've figured out how to solve this problem. And then a whole line of these different types of refrigerants came along that didn't have chlorine in them. This was in the 90s. So it took us about 10 years to figure out how to do it. And then you started to see it, go throughout the market, and they're used worldwide today. And this is from 2016. And so this was, again, a paper published in Science. And remember, we started this story, and here the ozone concentrations over the Antarctic were about 300 parts per million in the 1950s and 60s. And then as they had the technology in the 70s to start measuring those concentrations, which are these little white dots, you can see how the ozone concentrations were decreasing until we started to replace those chlorofluorocarbons with the new refrigerants, which kind of came online in the 90s. And then everything started to stabilize, and the concentrations of ozone stopped declining. And then if we fast forward to where we are today, this red line is a model. And the model is fitted with both the experimental data and some assumptions. And the model is predicting where the ozone concentrations will go. And it will take to about 2100 before the ozone concentrations over the poles are back to where they were in the 50s and 60s. And there's very good evidence. There's other papers that have been published since this paper in 2016 that show that the ozone concentrations are increasing again. So we solved that problem. But there's some important things to look at on this graph. Look how fast the ozone concentrations were decreasing. Like if we had done nothing, I'm guessing the ozone concentrations over the poles right now could potentially be 0. And the ozone concentrations over other parts of land, even the United States, would be declining right now. And there would be consequences, like you would have to limit your exposure outside. You might have to wear dark glasses all the time to be outside to prevent cataracts in your eyes, etc. Like it was a serious, serious problem that we were able to resolve because we had the science, we had the ability to be able to identify the problem, and then the science and the technology to resolve it. And then the other part of this graph that I'd like you to think about is that it only took, 40 years, 30 years for the ozone concentrations to decrease by over 50%, but it'll take more than 100 years for the Earth to recover. So you can fix these problems, but it can also take a long, long time for the Earth to heal and be back to where it was. So I say global challenges can be solved, but we got to work together too, right? It wouldn't do us any good if only the United States had said we'll sign the Montreal Protocol. 197 countries signed the Montreal Protocol because they believed. Now think about today and where we are in terms of what goes on the news, and can you imagine 197 countries coming together right now and agreeing on anything? Like it seems impossible. So now let's talk about present. So in December of 2020, Congress signed what was called the American Innovation and Manufacturing Act. And now the concern is not ozone and not ozone depletion, but global warming and climate change. And so as part of this American Innovation and Manufacturing Act, we're going to phase down refrigerants again, because refrigerants are also contributing to global warming. And this is where now the science and stuff that we're working on at KU. We have some ideas. I'll show you one, but I'm not 100% sure exactly how we're going to do this. Because another big part of refrigerants is not just their direct impact on our environment, but air conditioners, refrigerators use a tremendous amount of energy. In the United States, depending on the time of year, air conditioning and refrigeration use between 20 and 30% of all of our electricity. And you know that from your energy bills in July and August. I'm looking at my energy bill and thinking, gosh, what can I do to lower this energy bill? Could raise the temperature, right, in the house for sure, but you can't necessarily do that with your refrigerator. You've got to be able to keep foods and things cool and transport them, and medicines. So this is what we're now working on. How are we going to phase out all the existing refrigerants? What's in your car? What's in your refrigerator? What's in your house? What's in this building? What's in the Dillons? And then think about that all over the whole world. All that's got to change in the next 20 years. So this particular type of refrigerant, it's called a hydrofluoroolefin. This is what the molecule looks like. It's again more complicated than what we have today. It has this double bond in it, which makes its lifetime a lot lower in the Earth's atmosphere. And because it has such a low lifetime in the atmosphere, it also lowers its global warming potential. And so like I put in red sort of what the global warming potentials were for like the CFCs that we talked about, and now the gases that we use today. And they're pretty big numbers. CO2 is 1. So anything greater than 1 is what these are. So like what's in your automobile, what's in your air conditioner is 1,200 times more potent than CO2. And you hear a lot about CO2, right? But these gases are a lot more potent than CO2. Now, one difference is that we have billions of times more CO2 than we do these gases. But that doesn't mean we necessarily should neglect these gases. And in fact, these gases probably contribute to about 7% of global warming, whereas 90-some% of global warming is due to CO2. But because we phased these out once before, the belief is we can phase them out again and find a replacement. So this is one particular gas that we're looking at, has no ozone depletion potential, has a fairly low global warming potential, and it's being commercialized. If you have a pretty new car, like if you have a new Honda Accord that was probably made within the last 3-4 years, or a new Toyota Camry that was made within the last 3-4 years, it probably has this in it as the refrigerant. Or if you've bought a refrigerator maybe in the last 2-3 years, it probably has this as the refrigerant. So it's just starting to slowly come online. There's also mixtures of refrigerants. So like this is an air conditioner that probably looks like something that might sit outside your house. That has a mixture of these two gases. And in the grocery store, like Dillon's, in the supermarket display cases, that has a mixture of 3 different refrigerants. That complicates it even further because now we have to separate mixtures of refrigerants and not just the single gases. And it turns out that like in the US, there's about 120 million of these units. And each one of them has about 5 to 10 kilograms. So, you know, there's about 2 pounds per kilogram. So that's 10 to 20 pounds of refrigerant in your air conditioner and 120 million of them. Or in your grocery store like Dillon's, there's about 1,000 to 2,500 kilograms or 2,000 to 5,000 pounds of refrigerant in one grocery store. And there's about 65,000 grocery stores in the US. So we're just talking about the US. So millions and millions of pounds of these gases that are in just these 2 applications. And so students that I have, we're trying to figure out, well, what do we do with them? Because some of these refrigerants, some of these gases like this one, if we could separate it from this one, actually is a very, very good refrigerant that could be used, still be used. But how do you separate them? Especially when you've got this kinds of volumes. So here's a picture of some of my students. This is Kaylin and Abby and Andrew and Ethan and Kareem. Ethan finished with his master's degree. The others are all working on their PhDs. They're developing different types of technologies for being able to separate these refrigerant gases so that some could be reused and then some will need to be repurposed. And we're hoping that we can develop some new chemistry to be able to convert the ones that have high global warming gas into something that's low global warming so that it could be reused as a refrigerant in the future so that you don't have to destroy it. And I think that's the key, is that we want to create these circular economies so that we're not putting more stuff in landfills and certainly not putting more stuff in our atmosphere. And because these are gases, that's where most of it ends up. And the problem with that is you can't see it. If I had a cylinder of refrigerant right now and I opened the valve on the end, you could think of it as kind of like an aerosol can, right? You don't see it, right? But if I have a plastic bottle, I throw it on the ground. I come by your house and throw a plastic bottle in your front yard. Probably make you mad, right? Who's out there throwing plastic bottles in my front yard? Because you can see it. But I go to your front yard and take my refrigerant and the guy who comes and works on your air conditioner or your refrigerator and is out there and has got to fix it, well, you got to do something with the refrigerant in there. It takes time to take it out the right way. So the fastest way to do it is just open a valve and you're probably not around anyway, so you don't know. You don't know, right? that the gas is being released in the atmosphere. But that's what happens. And then you multiply that times millions and millions and millions of units, and that just contributes to more problems related to global warming. So the students are trying to figure out, how do we prevent that? And to prevent that, we need technology. We need technology that's affordable and that works, so that we can take these gases out, we can separate them, we can reuse the ones that are safe, and then we can recycle and repurpose the ones that need to be made into something else. So I won't get into a lot of the details of that, but we work with other people too. So like here at KU, we do measurements. We work with people at the University of Notre Dame that do modeling. We work with people at Texas A&M that do chemistry to make new materials. Remember that Emily is a chemist. She's the one making stuff that's in little small quantities. And then the engineers at KU are figuring out how to scale that up. We work with other people that are doing modeling that take into account things like the energy efficiency, so that the refrigerant is safe, but it also goes into a system that's more energy efficient than what you currently have today. And then we have to build them. We actually have to build demonstration units to prove that what we've designed actually works. So these are two more of my students, Julia and Arishi, and they're working on their PhDs. And so one of the things that we had to prove that we could do was separate these refrigerants. Nobody had ever done that. Nobody ever been able to figure out how to separate some of these refrigerants. So again, due to time, I'm not going to go into a lot of details, but the way it works, it's called extractive distillation. And you can think of distillation like if you ever go to a brewery or a distillery, they're separating water and ethanol. Well, these refrigerants, you can't separate that way. So we do something called extractive distillation, where we take a solvent and we bring it into this tower and we feed in the refrigerant, and we separate the refrigerants based on their solubility in the solvent. So if I have two refrigerants and one of them is really soluble in the solvent and the other one has no solubility in the solvent, I can separate them, because one will dissolve into the solvent and one won't. And then once I get them separated, I can take the solvent and heat it up and get the refrigerant back out of the solvent, so I can reuse the solvent over and over and over again. And so the students figured out how to do that. They figured out how to model it so that we could see whether it would work, and then we had to build it. So this is some pictures of what we built over at KU. So this is a tower. So this is about 30 feet tall. So this is where the solvent circulates around inside, and then they feed in the refrigerant, and they're able to separate the two refrigerants. And this is Kaylin. She just finished with her PhD. This is Felipe. This is sitting inside the control room where they control it. And so we now have demonstrated for the very first time that we can do this. Kaylin was really interested when she came to KU because she came here with a master's degree and her MBA. She wanted to start a company. So I couldn't make her any promises. We'll work on your PhD. We'll see where that leads to. And hopefully, if we develop something, we'll start a company together. So we did. So we started Icorium Engineering Company. It's right over here at KU Innovation Park, which you can see from the parking lot of the church. And she's now hired about 5 employees. And she now has commercial contracts with some of the largest refrigerant producers in the United States that want this. They know, like, we have to have this. If we're going to separate these refrigerants and reuse some and phase out all the existing refrigerants, we can't do it without this technology. And so, like, an example is this is what's in your air conditioner, these 2 refrigerants. So now with that technology, they can separate those 2 gases, and those gases can go into new products that can be resold And these new products, which is what's nice about them, is it lowers the global warming potential, but also those new products can go in existing equipment. So you don't have to change anything about your air conditioner. So someone comes out to your house and takes this out, it'll go to them, they'll separate it, they'll send it to the companies to make these new products. Those new products will go right back in. And that'll be what will be used probably for the next 10 to 20 years in air conditioners that are going to be sold. I'll close with just a couple last slides. So you may have heard about this proposal that I was working on. So I worked on this proposal for like the last 2 years. We're very close to finding out the answer. We'll probably hear in May if we win this proposal. So this is with the National Science Foundation. We propose that we're going to do more of what you just heard, but on a larger scale, designing not only safe refrigerants, but more energy efficient air conditioners, better ways of doing dehumidification, and that'll all be part of a new center that will be at KU, but we'll have these other partners. So again, the people at Notre Dame will do modeling. The people at Maryland build systems like air conditioners. The people at Hawaii do climate modeling and climate science so that they'll be able to understand some of the things that I was showing you earlier. People at South Dakota and Lehigh are chemists, so they'll be the ones making these little tiny amounts and sending them to us to figure out how to make it on a large scale. And all of this is to create a circular economy for refrigerants so that as we phase out the existing refrigerants and replace them again for the third time, that we don't have to ever do this for a fourth time. Let's get it right. Let's spend the 10 years that it'll take to figure all this out. Hopefully one day you'll have an air conditioner that's very different than what you have today, that maybe uses half the amount of energy. But it'll take time to figure that out. And so we went to the National Science Foundation 2 years ago. We wrote a proposal. They liked it. 6 months later, they asked us to write another proposal. That was almost 1,000 pages. They liked it. They wanted to come visit us at KU. They came in September. There was about 200 people. They liked it. Then they asked us to come to Washington in December, present to them again. They liked it. So now we're just kind of waiting for them to make their final decisions. They picked maybe like 3 or 4 teams about every 2 years. There was about 200 teams that started, and we're probably down now to like less than 8. So we have probably about a 50% chance. It's a large amount of money for them. It's the largest amount of money they give. It'll be $50 million over 10 years. And with the companies involved, it'll be $100 million over 10 years to really figure out how do we make something that looks very different than what's outside your house today, that can cool it and do it with half the amount of energy. And so that's kind of what this proposal is all about, and making it circular so that the materials can be used over and over and over again. And so it also involves a lot of different disciplines. We realize that this isn't just chemists, and this just isn't engineers. Like, we have everybody from business to psychology to history to entrepreneurism, geography. It'll be 42 faculty across those 6 universities, across actually 16 different disciplines. Because you also have to change behavior. How do you change the person who comes to your house and says, all I got to do is open this valve and psh, versus using a new technology to recover it and recycle it, right? There's as much psychology there as there is science. And so that's why we've brought together a really unique set of disciplines to work on this. So just concluding remarks, air conditioning, refrigeration, essential to our quality of life. Current refrigerants are being phased out due to concerns over global warming and climate change. We're developing new technologies and new companies like the one I showed you that Kalen's running to recycle refrigerants rather than vent them to our atmosphere. And then the University of Kansas is working with these other universities to create a new center funded by the National Science Foundation that will hopefully be able to bring all this together. So I like this picture of Earth. You know, we all live on a planet, and it's called Earth. That's also why we named our program Earth, which actually is an acronym, Environmentally Applied Refrigerant Technology Hub, EARTH. NSF actually liked Earth too. Hopefully that's another reason we win the award. But like, we have to take care of this, you know. This is really all we have in terms of a place to live. We might have a little colony on the moon one day. We might have a little colony on Mars one day. But it's certainly a place I'd like to go visit, but it's not a place I want to stay. You can't go outside. There's no atmosphere. You can't smell the flowers or hear the wind blowing through the trees because you have to be indoors, right? So, I mean, this is what we have. This is what God gave us, and we have to take care of this. So, all the work that I talk about is done by students and postdocs. You know, I tell people that as a professor, I'm more like a choir director. They're the ones that play all the beautiful instruments and make all the beautiful music, and I just stand up there and, you know, pretend like, you know, and try to guide them, but it's really them that do it. So with that, I'd be happy to answer any questions in the last 5-10 minutes that we have.
Excellent lecture.
Thanks.
I'm a chemist.
You're the one making this.
The person who did the ozone area at first, Sherry Rowland,
Yeah.
was a professor here also.
He was.
Yes.
Yes.
And he also won the Nobel Prize.
He did.
So there you have something to look forward to.
Yep, that would be awesome.